In geometry, parallel lines are lines in a plane which do not meet, that is, two lines in a plane that do not intersect or touch each other at any point are said to be parallel. By extension, a line and a plane, or two planes, in three-dimensional Euclidean space that do not share a point are said to be parallel. However, two lines in three-dimensional space which do not meet must be in a common plane to be considered parallel, otherwise they are called skew lines. Parallel planes are planes in the same three-dimensional space that never meet. Parallel lines are the subject of Euclid's parallel postulate. Parallelism is primarily a property of affine geometries, and Euclidean space is a special instance of this type of geometry. Some other spaces, such as hyperbolic space, have analogous properties that are sometimes referred to as parallelism. Symbol. The parallel symbol is, for example, indicates that line AB is parallel to line CD. In the Unicode character set, the parallel and not parallel signs have code points U plus 2225 and U plus 2226, respectively. In addition, U plus 22D5 represents the relation equal and parallel to Euclidean parallelism. Two lines in a plane. Conditions for parallelism given parallel straight lines L and M in Euclidean space. The following properties are equivalent. Every point on line M is located at exactly the same distance from line L. Line M is in the same plane as line L but does not intersect L. When lines M and L are both intersected by a third straight line in the same plane, the corresponding angles of intersection with the transversal are congruent. Since these are equivalent properties, any one of them could be taken as the definition of parallel lines in Euclidean space. But the first and third properties involve measurement, and so, are more complicated than the second. Thus, the second property is the one usually chosen as the defining property of parallel lines in Euclidean geometry. The other properties are then consequences of Euclid's parallel postulate. Another property that also involves measurement is that lines parallel to each other have the same gradient. History. The definition of parallel lines as a pair of straight lines in a plane which do not meet appears as definition 23 in Book 1 of Euclid's Elements. Alternative definitions were discussed by other Greeks, often as part of an attempt to prove the parallel postulate. Proclus attributes a definition of parallel lines as equidistant lines to Posidonius and quotes Geminus in a similar vein. Simplicius also mentions Posidonius' definition as well as its modification by the philosopher Agoniz. At the end of the 19th century, in England, Euclid's Elements was still the standard textbook in secondary schools. The traditional treatment of geometry was being pressured to change by the new developments in projective geometry and non-Euclidean geometry. So several new textbooks for the teaching of geometry were written at this time. A major difference between these reform texts, both between themselves and between them and Euclid, is the treatment of parallel lines. These reform texts were not without their critics, and one of them, Charles Dodgson, wrote a play, Euclid and His Modern Rivals, in which these texts are lambasted. One of the early reform textbooks was James Morris Wilson's Elementary Geometry of 1868. Wilson based his definition of parallel lines on the primitive notion of direction. According to Wilhelm Killing, the idea may be traced back to Leibniz. Wilson, without defining direction since it is a primitive, uses the term in other definitions such as his sixth definition. Two straight lines that meet one another have different directions, and the difference of their directions is the angle between them. Wilson in definition 15 he introduces parallel lines in this way: straight lines, which have the same direction, but are not parts of the same straight line, are called parallel lines. Wilson Augustus de Morgan reviewed this text and declared it a failure, primarily on the basis of this definition, and the way Wilson used it to prove things about parallel lines. Dodgson also devotes a large section of his play to denouncing Wilson's treatment of parallels. Wilson edited this concept out of the third and higher editions of his text. Other properties, proposed by other reformers, used as replacements for the definition of parallel lines, did not fare much better. The main difficulty, as pointed out by Dodgson, was that to use them in this way required additional axioms to be added to the system. The equidistant line definition of Posidonius, expounded by Francis Cuthbertson in his 1874 text Euclidean Geometry, suffers from the problem that the points that are found at a fixed given distance on one side of a straight line must be shown to form a straight line. This cannot be proved and must be assumed to be true. The corresponding angles formed by a transversal property, used by W. D. Cooley in his 1860 text The Elements of Geometry, simplified and explained, requires a proof of the fact that if one transversal meets a pair of lines in congruent corresponding angles, then all transversals must do so. Again, a new axiom is needed to justify this statement. Construction. The three properties above lead to three different methods of construction of parallel lines. Property 1. Line M has everywhere the same distance to line L. Property 2. Take a random line through that intersects L in X. Move point X to infinity. Property 3. Both L and M share a transversal line through a that intersect them at 90 degrees. Distance between two parallel lines. Because parallel lines in a Euclidean plane are equidistant, there is a unique distance between the two parallel lines. Given the equations of two non-vertical, non-horizontal parallel lines, the distance between the two lines can be found by locating 2 points that lie on a common perpendicular to the parallel lines and calculating the distance between them. Solve the linear systems and to get the coordinates of the points. The solutions to the linear systems are the points, and these formulas still give the correct point coordinates even if the parallel lines are horizontal. The distance between the points is which reduces to when the lines are given by the general form of the equation of a line. Their distance can be expressed as two lines in three-dimensional space. Two lines in the same three-dimensional space that do not intersect need not be parallel. Only if they are in a common plane are they called parallel, otherwise they are called skew lines. Two distinct lines L and M in three-dimensional space are parallel if and only if the distance from a point P on line M to the nearest point on line L is independent of the location of P on line M. This never holds for skew lines. A line and a plane A, line M, and a plane Q in three-dimensional space, the line not lying in that plane, are parallel if and only if they do not intersect. Equivalently, they are parallel if and only if the distance from a point P on line M to the nearest point in plane Q is independent of the location of P on line M. Two planes. Similar to the fact that parallel lines must be located in the same plane, parallel planes must be situated in the same three-dimensional space and contain no point in common. Two distinct planes Q and R are parallel if and only if the distance from a point P in plane Q to the nearest point in plane R is independent of the location of P in plane Q. This will never hold if the two planes are not in the same three-dimensional space. Extension to non-Euclidean geometry. In non-Euclidean geometry, it is more common to talk about geodesics than lines. A geodesic is the shortest path between 2 points in a given geometry. In physics, this may be interpreted as the path that a particle follows if no force is applied to it. In non-Euclidean geometry, the three Euclidean properties mentioned above are not equivalent, and only the second one, since it involves no measurements, is useful in non-Euclidean geometries. In general geometry, the three properties above give three different types of curves: equidistant curves, parallel geodesics, and geodesics sharing a common perpendicular, respectively. Hyperbolic geometry. While in Euclidean geometry two geodesics can either intersect or be parallel, in hyperbolic geometry, there are three possibilities. Two geodesics belonging to the same plane can either be intersecting, if they intersect in a common point in the plane, parallel, if they do not intersect in the plane, but converge to a common limit point at infinity, or ultraparallel, if they do not have a common limit point at infinity. In the literature, ultraparallel geodesics are often called non-intersecting. Geodesics intersecting at infinity are called limiting parallel. As in the illustration, through a pointer not on line L, there are two limiting parallel lines, one for each direction ideal point of line L. They separate the lines intersecting line L and those that are ultraparallel to line L. Ultraparallel lines have single common perpendicular, and diverge on both sides of this common perpendicular. Spherical or elliptic geometry. In spherical geometry, all geodesics are great circles. Great circles divide the sphere in two equal hemispheres, and all great circles intersect each other. Thus, there are no parallel geodesics to a given geodesic, as all geodesics intersect. Equidistant curves on the sphere are called parallels of latitude, analogous to the latitude lines on a globe. Parallels of latitude can be generated by the intersection of the sphere with a plane parallel to a plane through the center of the sphere. Reflexive variant. In synthetic, affine geometry, the relation of two parallel lines is a fundamental concept that is modified from the usage in Euclidean geometry. It is clear that the relation of parallelism is a symmetric relation and a transitive relation. These are two properties of an equivalence relation. In Euclidean geometry, a line is not considered to be parallel to itself. But in affine geometry it is convenient to hold a line as parallel to itself, thus yielding parallelism as an equivalence relation. Another way of describing this type of parallelism is the requirement that their intersection is not a singleton. Two lines are then parallel when they have all or none of their points in common. It has been noted that Playfair's axiom used in affine and Euclidean geometry is then equivalent to the statement that parallelism forms a transitive relation on the set of lines in the plane.